All right, let's get right into it. Welcome to today's explainer, where we're going to unpack the completely invisible infrastructure that makes our hyperconnected world possible. You ever stop and think about how millions of people can stream videos, send text messages, and make phone calls all at the exact same time without constant data traffic jams? Well, the secret actually lies in two fundamental engineering concepts: multiplexing and demultiplexing. And today, we're going to decode exactly how the whole shebang works. Now, to really grasp why this technology is such a massive game changer, we kind of have to look backward to the early days of telephony. Back then, every single telephone call needed its own dedicated physical pair of copper wires connecting the intercity switching centers. As demand exploded, the physical reality became an absolute logistical nightmare. As the source material brilliantly points out, the skies of all the major cities in the world literally grew dark with overhead wires. We obviously couldn't just keep adding a new wire for every new user, right? A more elegant solution was desperately needed. So the real puzzle here is figuring out how multiple users can equitably share a limited communication resource. We call this resource a communication channel. Think of a communication channel as a single pipe, or maybe a single lane on a highway, that's used to transfer electronic information from point A to point B. The ultimate engineering challenge is basically this: how do we allow multiple distinct signals to share this single pipe simultaneously without crashing into each other and scrambling the data? Here's the roadmap for today. We're going to hit the communication bottleneck, introduce MUX and DEMUX, explore frequency division multiplexing, dive into time division multiplexing, compare the two, and wrap up with the future of sharing. Starting off with Section 1, the communication bottleneck. Let's look at the fundamental problem of limited resources. It's the bottleneck driving all of this innovation. The ultimate goal of any communication system is to share a limited resource as efficiently as possible. But there is a catch. If different signals mix improperly on the same channel, it creates what engineers call crosstalk or interference, and that significantly increases the probability of errors. Imagine trying to listen to 3 different people talking to you at the exact same time. The noise just blends together and you can't understand a single word. Our systems absolutely must avoid this at all costs. Which brings us to Section 2, introducing MUX and DEMUX. This is where the magic happens. These are the ingenious solutions that cleared up our skylines and revolutionized data transfer. The basic flow goes like this. On the transmitting side, you have multiple sources generating data. A multiplexer, or MUX for short, acts like an incredibly fast traffic controller. It takes all these various inputs, combines them into one composite signal, and sends it down a single shared channel. Then, at the receiving end, the demultiplexer, the DEMUX, catches this composite signal and carefully sorts it all back out into the original separate signals, dropping them off at their correct receivers. All right, Section 3, frequency division multiplexing, or FDM. So how do we actually pull this off? Well, let's look at the first major technique, which has been around for decades. Think of the total available bandwidth of a channel as a large pie. With FDM, we carve up the frequency spectrum, and each individual signal gets its own specific dedicated slice of that pie, a frequency band within the larger channel. Because they're operating at different frequencies, they can travel down the exact same medium at the exact same time without stepping on each other's toes. And you know what? You interact with FDM technology every single day. You experience this every time you tune your car radio to a specific AM or FM station. The air around you is literally filled with dozens of radio signals sharing the exact same atmospheric channel. But because each station broadcasts on a slightly different dedicated frequency slot, you can rock out to your favorite station without hearing the jazz station from the next town over bleeding into it. Now, carving up the frequency isn't a totally flawless system. Sometimes signals kind of bleed over into the adjacent lanes. To keep those radio stations or TV channels from interfering with one another, engineers use something called guard bands. This is basically empty, unused buffer space placed purposely between the assigned frequencies. It's exactly like the physical concrete barrier between lanes on a highway. It wastes a tiny bit of space, sure, but it guarantees a smooth, interference-free ride for the signals. Moving right along to Section 4, time division multiplexing, or TDM. Let's look at the second major multiplexing strategy. If FDM was all about sharing space, this next method completely flips the script. It shares time. Instead of giving everyone a dedicated lane, TDM gives everyone a dedicated turn. The system has signals A, B, C, and D, taking turns slipping their data onto the main line through a rotating switch. It's almost like a super fast revolving door. The channel is fully dedicated to signal A for a microsecond, then B, then C, then D, and then the whole process repeats. So instead of sending everything all at once in parallel, TDM weaves little pieces of data together, one by one, sequentially. This one complete cycle, where every single input gets exactly one turn to transmit a snippet of its data, is what we call a frame. By spinning that revolving door incredibly fast, it creates the perfect illusion to the end user that their connection is continuous and uninterrupted, even though it's technically pulsing on and off. There is a pretty huge catch here, though. Timing is absolutely everything. Because the data is chopped up purely by time, the sender and the receiver must be in perfect total synchronization. The DEMUX at the receiving end needs to know exactly when signal A ends and signal B begins. If the clocks are even slightly off, actually literally even a fraction of a millisecond off, the receiver will piece the data back together completely wrong, resulting in total chaos. To fix this, engineers embed special marker pulses just to keep the two ends locked in perfect rhythm. Now for Section 5, comparing FDM and TDM. Okay, so we've got these two heavyweights, two very different solutions to the exact same problem. How do they actually stack up? It's all about picking the right tool for the job. FDM is generally better suited for older, continuous analog signals, like traditional radio. It divides up the bandwidth, uses guard bands for safety, and is subject to what's called wideband fading. TDM, on the other hand, is the absolute champion for handling the crisp, discrete, digital information we rely on today. It divides up time, uses guard times between pulses, and deals with narrowband fading. And finally, Section 6, the future of sharing. Let's bring this all back to the modern digital systems that are quite literally powering our world right now. As we've transitioned to a purely digital landscape, digital multiplexing has completely taken center stage. We aren't just sending simple voice calls anymore. A digital multiplexer merges computer data, digitized voice, and high-definition video bit by bit onto massive, single, high-speed transmission lines, like fiber optic cables. By dynamically interleaving these digital ones and zeros, we utilize the full available channel bandwidth flawlessly without wasting a single drop of capacity. It's honestly a marvel of engineering. We went from skies physically darkened by heavy copper wires to billions of digital streams flowing seamlessly through thin air and fiberglass. The next time you stream a 4K video while simultaneously getting a text message and downloading an update, just take a second to appreciate those invisible traffic cops, the MUX and DEMUX, making it all happen without a single crash. Seriously, think about it. How many thousands of multiplexed signals are silently passing through your device at this exact second? It is a busy, invisible world out there. Thanks so much for joining me on this explainer, and keep your curiosity switched on.